Thanks, Kar. Thanks for inviting me, and it's my pleasure to talk about this work. It's joined with a lot of excellent people who've helped me through this journey. So I definitely got started along this with the people on the left. We call ourselves the Baccarati group. So Rina Barber, Emmanuel Candes, and Ryan Tipshirani, and and more recently, this is work with a future colleague of mine, Arun Kumar Kochi Botla, who'll be joining our department in fall, and one of my PhD students, Chirag Gupta. Okay, so let's get started. Let's see. Okay, so I'm going to start off. Broad outline of the talk is I'll tell you first what predictive inference is supposed to mean. What does that? Yeah, it's a term used in statistics often, but not that commonly known in machine learning. I'll describe some methods for assumption-free predictive inference, and I'll describe what it I'll wrap, and I'm sure several of you might also find those interesting. Okay, so let's get started. So what is prediction? So prediction is just, well, I'm in the standard setup. I'm going to think about standard regression through this whole talk. So here you have some training data x1, y1 to xn, yn. We have a new point xn plus 1, and we would like to predict its label yn. So think of real valued y's for the moment. That's definitely simpler for most of the talk. So this is how prediction usually proceeds. We have an algorithm A. This algorithm takes in the training data and spits out a predictor, which is a mapping from x to y. And so we think of an algorithm as just a mapping from some number of labeled data points. So it takes in one or two or three or any an unbounded number, some number of labeled pairs x and y, and it spits out a predictor, which is a mapping from x to y. Okay, so we get this predictor, and we use this predictor to predict the label, and the label is just a of xn plus 1, which is in the y space. So that's prediction. So how does that differ from predictive inference? So predictive inference says, well, we don't just want to point prediction. We would like an uncertainty guarantee. Don't give me a point, but give me a set. And the type of guarantee I would like is that with high probability, yn plus 1 is in this set, which I'm going to call C of xn plus 1 for the rest of this talk. If y is an interval, if y is real valued, then C of xn plus 1 could be an interval. But in general, C of xn plus 1 could be any set that contains yn plus 1 with high probability. So this is how we're going to try to capture uncertainty of our predictions, which is moving beyond the point to say, okay, this is how uncertain we are about our prediction. So why do we care about predictive inference? So why would we want a guarantee like the kind I've mentioned? Here's a simple example. Let's say that y is the time taken to get to the airport, and the covariates are, this is the time of the day, maybe the weather, things of that kind. So if I just give you a point prediction, or I'm trying to predict the conditional mean, and I give a prediction of 80 minutes, it's not very useful, because 80 plus or minus 5 minutes is very different from 80 plus or minus 40 minutes. So if you tell me how uncertain you are about your predictions, I'm going to act very differently. So, of course, if it's plus or minus 5, I might leave at a certain time. But if you tell me it's plus or minus 40, I might choose to leave earlier to hedge myself against the risk. So, so broadly, to make real-world decisions based on predictions, we do need to quantify uncertainty of those predictions. And so that's why we're going to be, in this talk, moving away from predicting a point to predicting a set. All right, so let's get a little bit deeper. Like me, I often get asked this question: what is the difference between a prediction interval and a confidence interval? And so I just want to just informally describe that over here. I'm not going to try to be too formal, but as we said, a predictor or a prediction algorithm is just a mapping from some number of labeled data points to a predictor, and a prediction interval of set is what we have defined earlier. The probability that yn plus 1 lies in my set is at least 1 minus alpha. But when we think of confidence intervals, we think of something else. We usually think that there's some set of underlying parameters, let's call, and there's a parameter space theta, and we have an estimator or an estimation algorithm that takes in some number of labeled data points, and it spits out some estimator theta hat, which is in the set script theta. And a confidence interval would be a subset of script theta. And I would say the probability that theta, which is this underlying true parameter, lies in my set Cn is at least 1 minus alpha. Now, the one difference between these two is that usually to associate some models, to associate some parameters, we have to make some model assumption. We need to assume some model relating y to x, or in general, some model that captures the joint distribution of x and y, and theta is usually some functional of that distribution. And so we would need to assume some model, and theta is some subset of those model parameters. Maybe we assume a linear model, we could assume a more complicated model, but you have to go with a model assumption. But when you do predictive inference, or the prediction interval as I've defined above, there isn't an underlying model that we need to assume. And we will be able to get guarantees of the kind desired without assuming a true model exists, or without any reference to a true model also. So somehow, that's one difference between a confidence and a prediction interval. Another difference is that often we expect that, as the number of samples goes to infinity, the volume of my confidence set will go to 0. I mean, this is maybe some, we would expect consistency of some kind, and this is one notion of, one way of capturing uncertainty. But this will not be the case ever with prediction intervals. So the best possible prediction interval an oracle would have is it would take the conditional distribution of y, given that x is xn plus 1. So that's some distribution. It would take the 1 minus alpha level set of this distribution, and that's the best possible oracle set, and that has some non-zero volume, and so the volume of any set we construct must be larger than that, and as n goes to infinity, it will converge to that non-zero value, and there's no way around that. So there's going to be some inherent unpredictability of y. Like, even if we had an infinite number of samples, for a new point we will never be able to predict y perfectly. There'll always be some amount of noise we won't be able to capture, and so that's also maybe a difference between prediction and confidence intervals. But in my head, the major difference is, for confidence intervals, you have to ask, what am I producing a confidence interval for? And you say, well, for some parameter. Well, what parameter? Well, there's some model and so on. So you have to assume some model. But for a prediction interval, you'll see that we don't need to assume a model. Yes, go ahead.
So I guess, you could go after some function of the distribution. For example, if you assume the data are IID, you could take your parameter to be the limiting relative frequency that the pair x and y fall in some set, right? And these sorts of parameters are always going to exist, say, under an IID model.
Sure. I mean, that's why I said this was not a formal difference. So there are confidence intervals which maybe you can define a little bit more non-parametrically. But I just want to differentiate it from a prediction interval, which hopefully at least the intuition of what is the difference between a confidence and a prediction interval came across.
Sorry, I missed you were just trying to give a high level.
Yeah, just like, what is the, like, people keep asking, what is the difference between confidence and a prediction interval? And sometimes, they swap the phrases. They'll say, can you give a confidence interval for y? Well, we're not trying to do that. We're trying to give a prediction interval for y. So I just want to clarify that difference. That's all.
Thank you.
Yeah. Okay, so what is the goal of assumption-free predictive inference? Okay, so it's going to be stated as follows. So we're going to be given some data, x1, y1 to x and y, and some labeled data. We're going to assume it's, for now, let's say that it's coming from some joint distribution pxy, which I'm going to call px as the marginal and py given x as the conditional of y given x. So we're given this data. And we have some algorithm in mind, but all of this framework broadly is going to be algorithm agnostic. But as I said earlier, an algorithm is just a mapping from our training data to a predictor. Um, Now, what do we want to do with this data and this algorithm? We would like to say that given a new point, xn plus 1 coming from px, I would like to produce a set, c of xn plus 1. And now this set is going to depend, of course, on the algorithm you choose to employ to construct the set. It's going to depend on the underlying training data dn. But I'm going to suppress that so that I don't have to keep writing c of a dn of xn plus 1. I'm just going to write c of xn plus 1. And so I would like to produce this set such that it has the guarantee of coverage, but this guarantee holds for all p of xy and for all algorithms A. So in some sense, if pxy is nice and my algorithm was smart, then the size of c of xn plus 1 will be smaller. If pxy is horrible, like heavy-tailed and discontinuous and terrible, and or maybe my algorithm was nonsensical, then this guarantee will still hold, but maybe c of xn plus 1 will be larger than we would like. So this is, in some sense, some kind of robustness to assumptions. We would, in practice, we would like to make some assumption about p of xy and some, design an algorithm based on that assumption. But the kind of guarantee we'll hope for is that even if those are assumptions that we made are wrong, no matter what the underlying pxy is, and no matter what the underlying algorithm is, the produced set will have this guarantee. Okay, so essentially, this is what we mean by assumption free. We will not make any assumptions on pxy, and we will not make any assumptions on a. A could be absolutely ridiculous. Obviously, in practice, we will see we won't do something ridiculous. We'll do something somewhat sensible. But you are free to use your own adversarial A and give me your own adversarial pxy, and yet the set I produce will have this guarantee. Obviously, the size of C will depend on pxy and on A. Okay, so some remarks. So this field, you can say, this subfield of producing uncertainty quantification without assumption was started by Vovk, Schaefer, and many others, and they've been doing it for about 20 years. I don't know why I have 19. That should be 20. So they've been, they set the foundations of this field, and almost everything we do now is, in some sense, stems back to what they did, for the last 20 years. So even though maybe I won't bring up their names throughout this talk, and I'll be talking a lot about my own recent work on this, I think they deserve, a huge amount of the credit. Some other remarks, we don't actually need the data to be IID from this joint distribution PXY. We just need the data to be exchangeable. So if you're not familiar with exchangeability, intuitively you can think about relabeling not really mattering. Doesn't matter which I called 1 and which I called n. Formally, it just means that every permutation of the data, they have the same kind of distribution. So we don't need them to be IID. This notion of having this algorithm in there is completely optional. Like, I could have stated the problem without reference to any algorithm. I could have just said, given some data, produce a set such that for every pxy, y is contained in cfx. So I could have stated this. We're going to use algorithms to help us, and so when we use algorithms to help us, I wanted to make it explicit that this will hold true for any algorithm, and we'll not make any assumptions about our algorithm matching well with pxy and so on. And this algorithm will be assumed permutation invariant, which means that if I relabel the data points and give it, it kind of gives me the same output. If it's a randomized algorithm, that's also fine. It gives me then the same distribution over mappings from x to y. An obvious point is that this statement is trivial without a size or efficiency requirement. I mean, I can always let c of xn plus 1 be the whole script y, and then this probability is equal to 1. So, this is always true. So intuitively, what we're going for is we're trying to find small sets C such that this still holds. In fact, we will want to construct things where this probability is equal to 1 minus alpha. So we will hope for not overcovering, and we'll show you that we'll be able to achieve that quite reasonably. This probability statement that's written is actually over all of the training and test data and randomness in the algorithm. So this PR is really over x1, y1 to xn, yn, and xn plus 1, yn plus 1, and any external randomness you might have when you derived your algorithm. So that's what that probability is on the left-hand side. And we would like that probability to be at least 1 minus alpha. So I mean, that's standard, but just making that clear. The more important part is that this statement is not being made conditional on xn plus 1. Okay, and I'll come back to that on the next slide. That's extremely important. This is a marginal prediction interval. It's not a conditional prediction interval. And it's important to emphasize that. So I'll state that on the next slide. Essentially, conditional coverage is impossible without assumptions on pxy. This is a provable statement. Okay, so what we will achieve is the first line, probability that yn plus 1 is in C is at least 1 minus alpha. What we are not going to achieve is that for all x, the probability that yn plus 1 is in C of xn plus 1 conditional on xn plus 1 equal to little x, that is at least 1 minus alpha. We will not be able to achieve the second. The second is called conditional coverage. And several authors, including Wolfke and others, and more recently, Lay, Wasserman, Rinaldo, and Tibshirani formalized this, that you can prove that assumption-free condition inference is impossible, which means if the second statement is true, then the expected volume of that set must be infinite. More recently, we ourselves have explored notions of approximate conditional coverage. You say, okay, well, this seems to be too strong a statement. What if you condition not on xn plus 1 equal to little x, but what if you condition on sets? What if you condition on sets of finite BC dimension, small subsets, but the class of subsets is limited? What if you condition on sets of mass at least that have Lebesgue measure at least delta? Does that help? So we've looked at notions of approximate conditional coverage. I will not be going into that in this talk, but you can find a reference to a paper on any of our websites. But morally, conditional coverage is impossible. Marginal coverage is what we're aiming for. What we would like is a method that gives good conditional coverage in practice, but theoretically at least gives you marginal coverage without assumptions.
Aaditya, I have one question. So you mentioned that the probability is over the algorithm. Do you have a distribution on the algorithm, the space of algorithms?
No. This is if you choose to employ a randomized algorithm. I mean, I won't. Like, you should think about an algorithm as being something like apply k nearest neighbors or apply ordinary least squares or something. But if you say, oh, what if I applied SGT to a neural net? Okay, then there's some randomization. Then so I'm not assuming it's easiest to think of deterministic algorithms, but if your algorithm is randomized, then this is a statement on average over the randomness.
Mm-hmm.
All right, so hopefully now we're all on the same page on what predictive inference means and what assumption-free predictive inference means. So now I'll go over a few classes of methods for assumption-free predictive inference, and I'll do this in a non-chronological order. So in some sense, there's a method called full conformal prediction, which is a little mind-numbing to think about sometimes. You have to, it's a framework. So to get used to that framework, I'll first talk about something that was developed later, which is called split conformal prediction. And then we'll go to full conformal prediction and other methods. Okay, so this is very easy, which is why I'm starting with it. So what is split conformal prediction? The original authors called it inductive conformal prediction, but I think it's easier to call it split conformal prediction. So you're given your training data. This is just their visualization as a bag. This is not them plotted on a two-dimensional space. So yeah, it was first proposed by Papadopoulos, Proedru, Wolfke, and Gammerman in 2002. They called it inductive conformal prediction, but more recently, Lay, Wasserman, Rinaldo, and Tibshirani, these are my colleagues at CMU, they called it inductive conformal prediction. Oh, sorry, they called it split conformal prediction, the latter authors. Okay, so what do we do? It's a very, very simple algorithm. So you randomly split the data into two parts. They don't have to be equal in size. You call the first part D1, the second part D2. On the first part, you produce your predictor. I'm just going to call that A, which is just script A, our algorithm applied on D1 gives me a predictor A. Using this predictor A, I'm going to define some holdout scores. Okay, so this is the usual kind of cross-validation kind of idea. I define some score on the xi yi's that are in the set D2 using my algorithm A. So one example of such a score is this residual, which is just yi minus a of xi. I take the absolute value difference. I mean, as I said, it's easiest to think about real valued prediction for the moment. And so these are held out residuals. So let R bar denote the set of all Ri's from D2. Okay, so these are just the held out residuals. Now, using this D2, I'm going to calculate the 1 minus alpha quantile of R bar. And if, just so that everyone's on the same page with what I mean by the 1 minus alpha quantile, it's just you sort all the elements of R bar. They're just real numbers. You sort them. And you take the element which is at rank 1 minus alpha times n2 plus 1 ceiling. Okay, so why it's exactly defined in this way, it's not really important, but this essentially, when you have some discrete set of numbers, you have to say, okay, which rank guy am I picking and so on. So this is what I explicitly mean by the 1 minus alpha quantile. Just sort them and take the guy which is at rank about 1 minus alpha fraction. Okay, so that's what you do with D2. And then you combine them. You just say C of xn plus 1, this is my prediction set. It's going to be centered at my point prediction. A of xn plus 1 is my point prediction, so it's centered there. And I'm going to add and subtract the 1 minus alpha quantile of R bar. So in some sense, this Q1 minus alpha R bar is supposed to tell me out of sample on a new point that this A has not seen, how much variation is there expected to be? Well, with high probability, about Q1 minus alpha. And so that's how much I'm going to add and subtract. And you can prove that without any assumptions on pxy or on the algorithm produced, that the probability that yn plus 1 is in C of xn plus 1 is at least 1 minus alpha. Okay, so hopefully the construction is straightforward and intuitive as well.
So yeah, this is straightforward. Is it also sort of easy to show that this works? It seems like it's so, but maybe I'm missing some complexity.
Yeah. We'll look at empirical examples, things like that. We'll understand this method a little bit more. Yeah, this is great. It works. It does work. It's a good idea. If you
but I'm saying the theory here seems straightforward.
Yeah, so I'll give you a proof in 2 lines. So I'm going to give you a proof right now. Hopefully that will clarify the argument. Okay, so why does this? So firstly, I've said it's at least 1 minus alpha, but the nice thing about it is you get an upper bound as well. So it's also at most 1 minus alpha plus 1 over n2 plus 1. So if you have enough number of samples, this is basically also at most 1 minus alpha. The reason that there's this small gap is just because of this discreteness of the quantile, that's all. So you are not getting something that has coverage 1, you're not getting something trivial, you're really getting 1 minus, you ask for 1 minus alpha coverage and you're getting 1 minus alpha coverage. Okay, so short proof of why this is true. So first thing to note is that, so the proof will be in this yellow font. The first thing to note is I can rewrite this prediction set in a slightly different fashion. I'll say I'm basically going to take all of the y's that are somewhat close to A. So what does somewhat close mean? I'm going to take all the y's that the distance from A of xn plus 1 is at most Q1 minus alpha of R bar. Okay, so that's just a rewriting of the set on the left. Okay, so that's the first thing to note. The second thing I'm going to do is I'm going to just pretend for a moment that you actually sampled xn plus 1, yn plus 1. You sampled that pair from that joint distribution, but you just hid yn plus 1. You just hid it from me. I don't see it. I just saw xn plus 1. But in a proof, you can just write down what is Rn plus 1. Rn plus 1 is just yn plus 1 minus A of xn plus 1. So the proof knows Rn plus 1. And the thing to note now is that R1 to Rn2, these held out residuals, and Rn plus 1, these are exchangeable because A was trained on the first half of the data, and all of these things in the second half and n plus 1, they're all well, we had assumed IID, but even if you had assumed they were exchangeable, that's fine. And so they're all exchangeable ranks. They're all exchangeable residuals. And so the question of does yn plus 1 lie in C of xn plus 1, is basically reduces to this question. Well, it wouldn't, meaning I would make an error if capital Yn plus 1 minus a of xn plus 1 was too large, if somehow it looked a bit too extreme, meaning that difference, which is Rn plus 1, is larger than Q1 minus alpha R bar. If that's the case, then I'll make an error. So you can ask, okay, is it likely that Rn plus 1 is larger than the 1 minus alpha quantile of R bar? Well, if these residuals are exchangeable, it means that the rank of Rn plus 1 is uniform. It's uniform on 1 over n2 plus 1. So 1 over n2 plus 1, 2 over n2 plus 1, 3 over n2 plus 1 till 1. It's uniform on those. So the rank is uniform. And so the probability that Rn plus 1 is in the extreme, meaning it's in the largest 1 minus alpha quantiles, that probability is just at most alpha. Okay, so the proof is literally one line. It's just there's nothing much to see. The construction is transparent, and the proof just uses the fact that they're exchangeable, and so the rank of one of them is uniform, and so with high probability it lies within the set given by the others. Okay, so it's not imperative that everyone understands this proof as being present right in front of you. You can dwell on it later on, but you can trust me for the moment. It's a one-line proof based on exchangeability. Great. Okay, so how does it perform? So here's a simple example that will enable us to look at the effect of the algorithm as well as the effect of how we define this residual. Okay, so this is an example from this LWRT 18 paper that I've written in the corner. This is Lev Osman, Rinaldo Tipshirani. It's a JASA paper. So here we have a univariate example. So X is univariate, plotted on the X-axis, and we have our Y, which is what we're trying to predict. And in these gray circles are the data that we've observed. And what you can see in this data is that it's heteroscedastic. There's very little noise on the left. There's a much more noise on the right, so it's heteroscedastic, and so this on the left here is what split conformal prediction will produce on this example. So here the algorithm being used is some cubic spline, and so it produces this thing in the red curve, and this what you'll notice is that so what I'm plotting it's not I'm plotting, what they plotted in the pink band is at every point X in, they made a very fine grid. You can say, take 1,000 points on X, and at every point you can ask, what is the prediction at this point? Okay, what is the prediction interval at each point? So really this should not be thought of as a band. It should really be thought of as like 1,000 different prediction intervals that are being plotted as I vary X for visualization. So one thing you'll notice immediately is that it has constant width. And the reason it has constant width is simply because of the way we define the residual. The residual was this, y minus a of x, and because we define things that way, we get a prediction interval that has constant width. But there's no reason we have to. We can define this residual any way we want, and so on the right they propose something called locally weighted split conformal, in which they define the residual slightly differently, and maybe I'll tell you how they do. On the left, it's what we saw earlier. On the right, it's you now learn two functions on the first half of the data. You learn A, which is the conditional mean. You also learn sigma, which is like a conditional variance. So you learn two functions on the first half of the data, and you define your residual to be yi minus a of xi divided by sigma of xi. And so if you define your residuals this way, I mean, everything in split in the proof still goes through, R1 to Rn2, Rn plus 1, they're still exchangeable and so on. Except now the form of the prediction intervals that you get will vary with sigma. So, and so if you learn a conditional variance that's different in the left and the right, you can incorporate that and you can get prediction intervals that vary with X. Okay, so so as you can see already, there are several things coming out over here. The one is that the way you define the residual is important. Second is what you do on the first half of the data is completely up to you. You can learn just one conditional mean function, or you can learn A and sigma, and you can do other things. there's several other things to note which are interesting as well. Is the difference between marginal and conditional coverage is important. So like both of these figures show that essentially they're both split conformal, so they both have marginal coverage, which means that if I drew a point x at random, then the probability that yn plus 1 is in C of xn plus 1 is at least 1 minus alpha. But the way it's achieving that marginal coverage is it's over covering in some part of the space, it's under covering in some other part of the space, but on average with high probability it will cover. So you don't have conditional coverage on the left top plot. You have better conditional coverage on the right top plot, but both of them have marginal coverage without any assumptions made on A or on the underlying distribution. And so the plots below are supposed to show exactly that. Like essentially the left plot shows the local coverage that you have. So the red curve shows that the local coverage on the left is near 1. The local coverage on the right drops to near 0.7. But on average, actually, it's about 0.9, which is what they're targeted for this example. And the locally weighted version is, well, it's basically about 0.9. The reason it just dips at the end is because at the end, I guess we're producing almost point intervals, and there's just some numerical instability in how you estimate local coverage. But if you actually ramped up the number of points, you probably find it flattening out at about 0.9. And then what you can see, the same thing with the length is also interesting. With the first type of residual, the length is constant. The length of the prediction into the size is constant with x. But with the locally weighted version, the size is smaller on the left and larger on the right, and so that varies. And so, the way you define the residual is, I mean, it's completely up to you. For any definition of a residual, all of the theory still goes through. Obviously, we will want to use our intuition to guide us in defining the residual sensibly, picking a sensible algorithm that would work well on the data, things like that. And that will give us hopefully marginal coverage assumption free. Even if our definition of residual was ridiculous, it will still give us marginal coverage. But hopefully if our definition was sensible, it will also give us conditional coverage empirically, not provably. Okay. So here's one step forward. So this is going to be an example from a NeurIPS 2019 paper. I'll describe it. So this is an example where both of the previous methods don't work well. So let's look at it. So here the data looks slightly different. So here it's still a univariate example, x with y is just a real number. But over here you'll see that y has very, very light tails in one direction. So under 0, it has extremely light tails. There is some variance. You'll see there's some points that are just underneath 0, but it has actually huge variance in the other direction. And in fact, this is a zoom in of the plot. If you zoom out, there are some values which are at 50, 60, and so on. And so, it's a very asymmetric kind of noise situation. And what you're seeing on the left is what the usual split conformal prediction with the residuals I first described are, just y minus a of x, the constant width residuals. That's what you get on the left, and the dotted line is the predicted mean function, the conditional mean. If you just use some kind of standard regression algorithm. On the right is what you get if you do some kind of locally weighted version, which we had discussed also on the previous slide, where you learn a and sigma. As you can see, it's not really capturing the structure either. So, while it had fixed the problems in the previous examples, in this example, it's not really able to make out this kind of asymmetry in the noise distributions, and it's heavy tailed, and it's not able to do these kinds of things. So, so it was this observation by Romano, Patterson, and Candace. In this paper is called CQR. It's called conformal quantile regression. And so I would say that their main contribution or their main observation is, if we're going after a prediction interval, why are we first trying to estimate the mean and then estimate the quantiles? Why don't we directly estimate the quantiles and correct them using conformal regression? So essentially that's what they did in this paper. They said, on the first half of the data, instead of learning a conditional mean function, we learn a conditional quantile function. So they did quantile regression on the first half of the data, and that's what I'm calling capital Q. It's still a function of the first half of the data. And so they learned two quantile functions, one at level alpha by 2, one at level 1 minus alpha by 2. And now if everything was perfect, those would immediately give you the answer. If everything was well calibrated and the assumptions went through for quantile regression, then we wouldn't need to do anything. But that's not going to be the case. Is that for quantile regression to work, there are some assumptions, and so whatever's returned, if I just return to you alpha by 2 to 1 minus alpha by 2 from the quantile regression, that won't actually have any assumption free guarantees. So what we'll do is we'll use conformal prediction as a wrapper to just fix the mistakes made by conformal prediction and made by quantile regression. And so the way they said they do that is they define this residual, which is slightly different. They said, okay, now we'll look at the maximum of q alpha by 2 of xi minus yi and yi minus the other one. Okay, so what is this trying to do? This ri could be now positive or well, it could be signed in either direction. And I guess the idea is that if you undercover, like if the original quantile regression gives you something smaller than needed, then you can use conformal to expand it. If your original quantile regression overcovered, then you can use conformal to kind of shrink it and to get exactly 1 minus alpha coverage like you had wanted. And so anyway, when they use these residuals with quantile regression, this is what they get. So on the left plot are the output on test data, that is on unseen data, the prediction intervals. Again, they've just taken a grid of x's and produced intervals at each point. This should not be interpreted as a band. It is not simultaneously valid over all x. It's valid on average over random draws of x from the same distribution. But as you can see, it's working much better. It's actually kind of learning these kind of quantiles. It's at different parts, it's behaving more locally. And so, the theory for it is just you get marginal coverage, but in practice, you get pretty good conditional coverage as well, sensible kind of prediction intervals. And again, on the right is the length of these intervals. As you can see, the red is split, the usual split with the earlier intervals where it's just constant width. The locally weighted does change the width, but it's somehow not capturing that you don't need to go in the other direction. But the CQR intervals, they don't really go below 0 that much, but above 0, so they're a little bit more asymmetric and so on. So it's a very cute idea. Essentially, I think doing quantile regression is somehow the right way, I think, to capture uncertainty and not do mean regression. It's much more non-robust to outliers and so on, but quantile regression, a little bit more robust to outliers and really going after the right quantities. And then conformal is really a wrapper on top of that to fix things. Okay, so that's split conformal prediction, and hopefully now you have some sense of the role of different algorithms. You can use mean prediction, quantile prediction, the role of different residuals, and things of that kind. And yet the proof is very straightforward that it works. I think now it's time to describe what was originally proposed by Vovk and others, and this is called full conformal prediction. I don't think about it as being very practical. There are certain special cases in which it is practical, but in general it isn't. But it's still an interesting, kind of thought-provoking framework. So let's just describe it. Okay, so as before, we're going to start off by saying, okay, we have this training data, labeled data that we have with us. And we have this new point, xn plus 1, where we're trying to make a prediction. So what they say is, now let's just guess a value little y. Okay, just guess. Like guess little y is equal to 3,220. And now put that into your data set. So your new data set is your n labeled points and xn plus 1 and 3,220, because that's your new data set. Now you learn a predictor on all of this labeled data together. So I'm going to call that a superscript y, because as we change this little y, the predictor will change. And so I'm going to call it ay. Okay, and so now we're going to do things as before, but now we're going to calculate in-sample scores, because we have not left anything for out of sample. We used all of our data. And so these in-sample scores are also going to depend on what little y I used. And so I'm going to call them, RIY, which is just, for example, yi minus ay of xi, like as we did before, but it could be any other residual function you can choose to define. And you have the n plus first residual also. So ry n plus 1 is just the residual of your algorithm ay on xn plus 1 comma little y. Okay. So now what's the idea? I'm going to let r bar script this y as before be all of these n+1 residuals, not held out but in sample residuals, and I'm going to let q1 minus alpha of r bar y denote the 1 minus alpha quantile of all of these n+1 quantities. Okay, so all of this thing is kind of similar notation to as before. And now what I'm going to do, this is the part that's a little mind numbing, is I'm going to repeat this procedure for every single little y in my space. Okay, so I mean, if script y is all of the reals, then you're going to repeat this morally, like, or in your head at least, you're going to repeat this procedure for every little y. You're going to guess, little y is 22 and little y is 1 billion. And you're going to do this, and you're going to retrain your predictor ay every time on a new data set where one point is different. But you're going to retrain your predictor. You're going to recalculate these residuals. You're going to recalculate these quantiles and so on. Okay. Now the final set that's output C of xn plus 1 is, I'm going to say it's all of the nice little y's. So what are the nice little y's? They're the y's for which the n plus first residual was not extremely absurdly large. So it's not in the 1 minus alpha quantile of the R bars. It's not larger than that. It's smaller than that. So those are the ones for which my little y guess was reasonable. So what's the broad intuition for this? Like, if little y was, let's say, close to capital Y n plus 1, it's close to y n plus 1, then all of these are going to be exchangeable residuals, and this Rn plus 1 will with high probability be less than the 1 minus alpha quantile of those Rs. If my little y was absurd, let's say that most of the data, the observations are like +1, -1, +2, -2, things like that, and I'm guessing little y as 1 billion, then what's going to happen is that very likely the n plus first residual will be 1 billion. It's going to be really huge, and it's going to be much larger than all of the others. Of course, this depends on the algorithm. I don't have the algorithm at this point is arbitrary, but intuitively that's what's happening. If you guess an absurd value of little y, the hope is that the n plus first residual looks crazy, and you'll be like, okay, I'm going to throw out this little y. It doesn't look reasonable. And whenever your little y was somewhat reasonable, it was kind of in the range of reasonableness around yn plus 1. And you'll be like, okay, the n plus first residual looks kind of reasonable, and so I'm going to keep this little y. I can't rule it out. And so the theorem, of course, is that without any assumptions being made, the yn plus 1 is in C of xn plus 1 with high probability. Okay, so that's full conformal prediction. Hopefully you see why I did not introduce this first. You just kind of have this thought experiment where you do something for an uncountably infinite number of times. As I said, in some special cases, like maybe for least squares, maybe for k nearest neighbor regression, you don't actually have to repeat these things, and you can perform these operations kind of implicitly. But for almost any other situation I can think of, maybe random forests or deep nets or many other settings, you're just going to have to actually retrain these things, and so it's not practical. So split conformal is actually practical. You only have to train the algorithm once. But conformal prediction in general is not practical, but you can come up with heuristics to do it, maybe grid up your space, things of that kind. So maybe I just wanted to present what the algorithm is.
Aditya?
Yep.
Could you, if there are any surprising hypotheses for this theorem, could you maybe just mention them briefly? Like, are there any restrictions whatsoever on the prediction algorithm?
No, nothing. No. This final statement is true for any prediction algorithm, and the idea, the proof is again one line. It really is. You just have to imagine. You have to look at the failure event. You have to ask, okay, why would yn plus 1 not be in C of xn plus 1? When could that happen? The answer is when I'm repeating this process for all possible little y's, one of those little y's happened to magically be capital yn plus 1. I didn't know this, but at one of those times I repeated it, one of them was yn plus 1. And now when I did this process for yn plus 1, I basically had n plus 1 exchangeable training data points. I had x1, y1 to xn, yn, and xn plus 1, yn plus 1. They were all exchangeable. So then I ran whatever algorithm, I don't care what the algorithm is, I ran some algorithm on them. But because the data points were exchangeable, all of the scores are exchangeable. and all of these residuals are exchangeable. So the 1 minus alpha, so the rank of Rn plus 1 is uniform among the others. And so the probability that Rn plus 1 is extreme is at most alpha. And so the proof really is one line. It mimics the proof of split conformal, or split conformal mimics the proof of this. It's just that, so I mean, morally speaking, there's no surprises here, but it's a little just take some thinking to understand what this process, what will it finally give you? Like for split conformal is very straightforward. If I use the residual y minus a of x, it'll actually just give me an interval, and I know what that interval is. It's an out of sample prediction, and I can take the quantiles. For this algorithm, you can't easily understand what kind of prediction set will finally be output. There's no guarantee that this is an interval. It can give you a union of many intervals, and okay, that's the set. So of course, for special cases, if A might be OLS or something of that kind, maybe you can show it is an interval, fine. But then split conformal always gives you an interval, and you can understand what it is. Full conformal for other more complex algorithms, it's unclear what it's actually doing. So that's one reason you might not want to use it, because maybe it's harder to get a grip of what it's doing. Another reason, which is somewhat intuitive to people who work with deep nets, is this will fail if you have an algorithm that can fit essentially that can fit all the data perfectly, no matter what the data is. So if you have an interpolating algorithm, which we are used to seeing these days, essentially what will happen is for every single little y that you give me, the algorithm AY will just fit all of the data perfectly, and every single residual will be 0. So every score will be 0, and there's no way for me to tell which little y was a bad idea and which little y was a good idea, because essentially I'm fitting all my data perfectly. No matter what little y I guess, I get all zeros, and so the prediction interval will be the whole real line. And I mean, if you can use some randomization in the case of ties to make sure you're not outputting the whole real line, but you're outputting something that has mass 1 minus alpha, but there's no reason that has to be sensible when you have an interpolating predictor. So that issue exists because we're using in-sample scores for full conformal, but that does not exist for split conformal because we're using out-of-sample scores. So even if you have an interpolating predictor on the first half, the out-of-sample residuals will be non-zero, and you can sort them, you can do stuff with them, so it'll actually give you something sensible. So there's actually several advantages in my computational as well as statistical to use split conformal over full conformal. But I think from a historical point of view, it's also good to know where these ideas stem from, and this is where they stem from.
Thank you. That was very clear. Quick follow-up question, which is that if I put in sort of capacity control on my predictor, can you start to get more guarantees about the nature of the confidence interval I'll get in the full conformal set?
Yeah. So yes. So if you make assumptions on PXY and you make assumptions on the kind of algorithm you're using, then you can prove kind of oracle properties of this set. That if you followed conformal prediction, this set will converge to some kind of oracle optimal set, or the volume of this set will converge to the oracle volume set, which is the 1 minus alpha level set of the conditional distribution. So yeah, so if you make assumptions on PXY and on the algorithm, then you can prove stronger guarantees. You can prove essentially efficiency guarantees. But without assumptions, we can at least get validity guarantees. Okay. All right. So again, over here, for the same reason, as long as the star means that as long as there are no ties, and that was true in the split conformal case as well, that as long as there are no ties in the scores, you can get an upper bound as well of 1 minus alpha essentially. But if you have ties, which is much more likely with full conformal than with split conformal, you can get an upper bound of 1, which is trivial. All right, so I'm just going to switch gears a little bit and say, well, we saw split and we saw full. Are there intermediate variants? Is there something like a leave one out variant, like a leave one out cross validation version, but for prediction intervals instead of for model selection? And so let's look at it. So a natural answer is given by what's called the leave one out Jackknife. And so this was, this is how it works morally. You take your training data, you have some prediction algorithm, script A, and and you train n predictors, each time leaving out one data point. So you apply script A on your data set when you leave out x1, y1. I'm going to call that a minus 1, and similarly to a minus I and a minus n. So you train the algorithm n times to produce n different predictors, and you calculate leave one out residuals. So this is like yi minus a minus I of xi. So what is a minus I doing on xi yi, which is out of sample for it? And then now you can call R bar this set of leave one out residuals. You can call Q1 minus alpha of R bar the 1 minus alpha quantile of these leave one out residuals. And you can ask, okay, here's the Jackknife interval that I would produce. It's A of xn plus 1. So that's my point prediction. And I'm going to add and subtract, instead of adding and subtracting the held out split conformal residuals, I'm going to add and subtract the leave one out residuals. And so this is called the Jackknife interval. And so this is kind of it stems back to Kenui in 47. Tukey in the 70s gave it the name of the Jackknife. It was a precursor to the bootstrap. It's a very natural idea. So you can ask, okay, does this work? Does this have any guarantees? Unfortunately not. You can quite easily construct a distribution and an algorithm for which the probability that yn plus 1 is in this set is actually 0. So you wanted 1 minus alpha, you got 0. Okay, so this is a case for math. Like intuition can only take you so far. At some point, intuition just fails. This is a very intuitive procedure, but it's wrong. So it doesn't have assumption-free guarantees. And so this is why we need math to kind of save us and get something that is provably correct. Okay, so I'm not going to describe the algorithm and the distribution that achieves this. You can imagine it's a construction. You actually have to construct it, but you can somewhat easily. You might wonder, is this construction likely to occur in real life? Are we likely to see such things in real life? We'll see an example where it does occur very naturally for OLS, and I'll come back to that in the simulations. But for now, this leave one out Jackknife idea without alterations has no guarantees. So recently we came up with a variant which is called the Jackknife Plus, and I've on this slide I've just rewritten the Jackknife for comparison. It's related to something called cross-conformal prediction that was introduced by Vovk and others, but it's maybe harder to describe that. So I'm going to describe our algorithm, which is called the Jackknife Plus. Okay, so this is the Jackknife as written so far. Now, the first thing to note is that you can rewrite this interval, a of xn plus 1 plus or minus this quantile. You can rewrite it slightly differently. Essentially, the left endpoint is the alpha quantile of a of xn plus 1 minus ri. Here, a of xn plus 1 is just a fixed constant, and it's ri that's varying. So you have r1, r2 to rn, and you take the alpha quantile of all of those numbers, meaning you sort them and you take the left endpoint, the alpha quantile of those numbers. And then the right endpoint of this interval is you take a of xn plus 1, add r1 to rn, and you take the 1 minus alpha quantile of those. So it's just a rewriting of the interval above. Okay, so essentially the reason why Jackknife fails, and that's exploited in the construction to show that it fails, is that there's a mismatch between A and Ri in this formula for the alpha quantile. Essentially, Ri was constructed using A minus I, but we're applying it to A, and we have not made any assumptions on how A and A minus I might be related. And so we're going to define the Jackknife plus interval as take the alpha quantile of some slightly different quantities. Now you take a minus 1 of xn plus 1 minus r1, a minus 2 of xn plus 1 minus r2, till a minus n of xn plus 1 minus rn. So you essentially, instead of taking a single point a of xn plus 1, you take n different points, which are these a minus I. So now you're matching the residual to this predictor a minus I, and you do the same for the right endpoint as well. Okay, so that's what we call Jackknife Plus. It's a super minor variant of Jackknife. And this is what we can prove. We can prove that without any assumptions, so for all distributions and for all algorithms, the probability that yn plus 1 lies in C jackknife plus of xn plus 1 is at least 1 minus 2 alpha. So this is joint work with, again, the Baccarati group. This was just accepted at the Annals of Statistics about a month ago, so it'll appear later this year. And so we have managed to fix the jackknife and give it some assumption-free guarantees while the original one did not. Okay, and so just for clarity, I will remove the original jackknife definition. So now you actually don't need this additional predictor A, but it's something very natural in the first step and something maybe slightly unnatural in the second step. Or I mean, it's natural in hindsight, but that's not what people have done so far. So so this is the fix that makes it work without assumptions. So here it's useful to visualize it. So this is a visualization of it. On the left is jackknife. Okay, so I've replaced A by mu hat. This is because I've copied the figure from the paper. But essentially what on the left is showing, this is what jackknife does. It centers the various intervals at the same point, mu hat of xn plus 1 or A of xn plus 1. It always centers at that point and adds and subtracts these different leave one out residuals. And then based on these various intervals you could perform, it takes the 1 minus alpha quantile of those. On the other hand, jackknife plus does something slightly different. It centers each of these intervals at a slightly different point. And so actually, if you take the 1 minus alpha quantile of those, it's likely to be a little bit larger, which is why it has some guarantees. It's a little bit more conservative, intuitively a little bit more conservative than jackknife. So what can you prove? Also, you can prove that obviously jackknife is centered at A of xn plus 1, so it contains A of xn plus 1. But jackknife plus, we can't say anything about A of xn plus 1 because we don't know what A does on n minus 1 points versus n points. We have not made any assumptions on the algorithm. So your algorithm could be for 34 points run random forest, for 35 points run k nearest neighbors, for 36 points run boosting. You know, your algorithm script A could be anything. It's just a mapping from some number of training data points to a predictor. So when you're making no assumptions about how the algorithm is changing with the number of points, you know, we can't say anything about whether A of xn plus 1 is in this. But what we can say is that it contains the median of A minus I of xn plus 1. These n points, it'll contain their median. So that's for sure. Again, this is related to something called cross-conformal prediction by Wolf. And what you can show is it contains so cross-conformal prediction need not return an interval. It can return, so cross-conformal is a variant of split and full conformal that also uses a leave one out idea. But cross-conformal prediction does not return an interval. It returns potentially a union of n intervals. And so we can show that the jackknife plus does contain the convex hull of those. So they're actually very closely related. And in fact, all of our proofs for jackknife plus also go through for cross-conformal prediction. So that's nice. So now you might ask, well, you know, you've made no assumptions on relating A minus I to A and so on. If you actually make some assumption of stability, now I don't want to go into this talk, but you can look at it in the paper. If you make some stability assumption about the algorithm, about how it does, you know, when you leave a point out and don't and so on, then both, you know, all three, jackknife, jackknife plus, and cross-conformal, they all have a coverage of at least 1 minus alpha. Okay, so actually you get 1 minus alpha coverage for all of them under stability. But if you're potentially working with unstable algorithms, then jackknife has no guarantees, and jackknife plus and cross-conformal give you 1 minus 2 alpha coverage. Okay, and we can actually produce an instance. So there is an example of a distribution and an algorithm for which we actually achieve 1 minus 2 alpha. So 1 minus 2 alpha is not a proof, I mean, something in the proof that we should have gotten 1 minus alpha, but we could only, you know, prove 1 minus 2 alpha. That's not the case. We know of an instance where it achieves basically 1 minus 2 alpha up to a, you know, 1 over n factor. But this is without stability assumptions. If you're willing to assume stability, it actually gives you 1 minus alpha. So this is what I would actually recommend kind of in practice is, you know, a jackknife plus approach, because it tends to perform well, and we'll see that in simulations. Okay, so here are some empirical observations that I think are somewhat enlightening. So let's go into them. So this is an example of, it's extremely simple so that, you know, everyone can be on the same page. It's ordinary least squares. So that's the underlying algorithm that I'll use for any n and d. I'll just run ordinary least squares. If n is larger than D, obviously we all know what OLS does. When n is smaller than D, there's many ways to define OLS. You can either say I'll start gradient descent at 0 and run it till convergence, or you can say I'll do ridge regularization and I'll take the ridge penalty to 0. There's many equivalent ways of defining what OLS is, but it's minimum norm least squares when n is less than D. Okay, so now what we're plotting over here is we always fix n as 100. So there's always 100 points, and we vary D. Okay, so D could be, it varies from 0 to 200, and we generate the data from a linear model with Gaussian noise. So Y is just X beta. So X is just randomly drawn from a Gaussian, a D-dimensional Gaussian, a spherical Gaussian, and then Y is drawn as X beta plus some standard Gaussian noise. And so it's the simplest of setups. The algorithm is OLS. Let's see what do these various different prediction intervals do. So this here I'm now plotting coverage against dimension. Okay, so let's go through these. So the first one is naive. Okay, so naive is this blue line that's kind of dropping off. So naive is I don't do any sample splitting, I don't do conformal, I kind of just do in-sample residuals, and I give you a prediction interval that uses in-sample residuals. Now obviously you can overfit, the in-sample residuals will be smaller than what you expect. So the naive intervals essentially have no coverage as you get to high dimensional settings. The second thing to notice is Jackknife. So that's the yellowish or orangish plot. So Jackknife has 90% here, alpha is 0.1. It gives you 90% coverage, but around D is equal to 100, where n is, when n is nearing D, that's when OLS is a very unstable predictor. That's when the covariance matrix starts to become extremely ill-conditioned. It's not really invertible at n equal to D, and so that's when it's an unstable algorithm. And you can see Jackknife, its coverage drops drastically. So it's like at about 90 or something like that, you can see this sharp drop in the coverage of Jackknife. It starts to get better, and actually, as we know, when n is sufficient, when D is actually much larger than n, then this minimum norm least squares actually becomes a stable predictor once again. So things are actually nice in the very high dimensional setting once more. So Jackknife again starts to perform well there. The green curve is Jackknife plus. And the thing to note in Jackknife plus is it gives you 90% coverage right through the whole regime. So whether it's unstable or stable, you asked for 90% coverage, you get 90% coverage. Now remember that the theory said that, well, only if it's stable, you'll get 90%. Otherwise, you might get 80%. You might get 1 minus 2 alpha. Well, we don't see that in this example. In this example, even though it's unstable around n equal to D, we still see 1 minus alpha coverage. So there's something more to understand about Jackknife plus. It seems to have some kind of additional stability beyond what we're able to prove, that it gives you 1 minus alpha, even though we don't know how to prove that it does. We know a low bound of 80%, but it gives you 90%. I would ignore the red curve, Jackknife min-max, it's something else. CV plus, this is a k-fold version of this. You can say, do I have to leave one out? Can I do a k-fold version of this? And the answer is yes. And so it turns out that the k-fold versions tend to overcover. So those are the purple plots that kind of have a larger coverage than what you'd expect. Split is in brown. It overlaps with green. So it has coverage basically at 90% the whole time. This is what we expect. Again, we can prove that we'll get 9%. And in this example, full conformal prediction has this problem that the residuals end up becoming 0. If you're in a situation where n is less than D, then ordinary least squares it'll perfectly fit the data. And so all of the in-sample residuals will be 0. So what you see is that it gets 90% coverage up to dimension 100. And then after that, it kind of spikes up and gives you a larger coverage. And we are truncating the Y so that we don't have to do a search over all of the real line. But essentially, the coverage will go to 1 when n is greater than D. Again, you can use randomization to give you 90% coverage again, but it's unclear what is the best way to do that randomization to give you a sensible interval. So here we're seeing that because it's an interpolator, when n is less than D, full conformal starts to suffer. Okay, so that's for coverage. All of this kind of makes sense. We can now look at width. So width is how large are these intervals across n and D. Okay, so the first thing again, we'll go in order. The naive intervals the widths are really small, and that's just because they don't have any coverage. So you'll see this blue line trailing off at the bottom means it doesn't have coverage, but it undercovers heavily. The Jackknife and the Jackknife Plus, the orange and the green line are extremely similar. So they're almost overlapping throughout the whole process, and so their widths are almost identical. They only differ kind of at n equal to d, and just around that point, if I was to zoom out, you would see that Jackknife Plus is slightly wider than Jackknife when it's unstable. So somehow Jackknife Plus takes into account the instability by looking at the variance among the A minus i's, and doesn't just center at a single point and says, well, if A minus i's can be very different, then I'm going to take into account that instability. So around that point, they're a bit different, but everywhere else, they're basically the same. So Jackknife Plus kind of fixes Jackknife at those unstable points. Split conformal prediction. And so another thing to see is this kind of double descent curve. This has become very popular in ML. We see this double descent curve where essentially in the low dimensional thing setting, the width is small. The width spikes up when n is equal to d. And then again, when you get into a really high dimensional setting, the widths actually become smaller. So somehow the d is equal to 200 is, and this is what we expect, of course, but d is equal to 200 is an easier problem than d is equal to 100 when you have 100 data points. And okay, so that's nice. Now, what you see with split, of course, split is spiking at 50, and the reason is because it's fitting ordinary least squares on 50 data points. And so when d is 50 and n is 100 and it uses 50 data points to fit, that's when it is unstable. And so its width spikes at 50, and it's actually very nice at 100. But all of the other methods, which are basically using 100 or 99 points or so on, they're spiking near 100 and are better near 150 or 200, they stabilize again. So all of these things are kind of things that we morally expect to see. And maybe another interesting thing is that full conformal prediction is not that much better or worse than Jackknife Plus. They're doing somewhat similarly initially, and then later on, full, we're not sure what to do with it because it gives you 0 residual, so you have to randomize. But essentially, initially they're very similar. So there's no need to take this huge computational cost of full. You can just do Jackknife Plus, and well, at least in this example, it does something almost identical. Okay, so any questions about this example? Okay, now I'll briefly describe a couple of generalizations. So, Kay, I have about 5-6 more minutes. Is that right?
Yes, you can go a bit over, but yes, we usually leave this at the end.
All right. Okay. Okay. So here's right now we have defined this Jackknife Plus. The way we defined it was using these residuals yi minus a of xi, so that we could use a minus I and so on. So it was somehow we wrote the paper kind of tuned to this form of a residual, but we would like to generalize this idea so that the Jackknife Plus idea works with kind of any form of residual. And we found that one nice way to do that was using this framework of what we call nested conformal prediction. So this is a slightly different viewpoint on the standard conformal prediction. So this is a different way to go about deriving conformal prediction. So you first start by saying, I'm going to specify a sequence of nested sets, and I'm going to call these ft of x. So they're they're based on some point x, which will be xn plus 1, and t is going to lie in some ordered set tau. Okay, and these nested sets are going to be such that when I use the inf over tau, I get the empty set, and when I get the sup over tau, I get the full set script y. Okay, so this is a sequence of nested sets from the empty set to the full set. Now, essentially, within this sequence of nested sets, so the sequence of nested sets I'm going to define using an algorithm to guide me. But if I fix a sequence of nested sets, there is a perfect or an oracle T star. And I'm going to call it T star of alpha, which is the infimum over T such that I get at least 1 minus alpha coverage. So obviously, if I have the empty set, I get 0 coverage. If I have the full set script phi, I get 1 coverage. There is some T star in there because it's a nested sequence, which is the smallest T for which I get 1 minus alpha coverage. Then essentially within this class of sets, you can think of f T star of alpha at xn plus 1. Within this class, this is kind of the oracle choice of, this is what an oracle would do if it was to to pick a nested set, one set from this nested set within this class. And what you can think of saying is, like, if we knew this mapping between T and T star of alpha, we would be done. Like, we would just pick T star of alpha every time, we would be done. But we don't know how to calculate T star of alpha. We don't know how to calculate this smallest T such that I get 1 minus alpha coverage. And so you can try to think of conformal methods as trying to estimate T hat of alpha, which is an approximation to T star of alpha, but using the data. So they're trying to get at this oracle calibration choice of T star. So that's one way to view what conformal prediction is doing. So, within this framework, you can put in many proposals in the literature for what the score functions should be. So you can say, what are these sets ft of x? What should they look like? I've shown you some examples in today's talk. So the first one is the usual residual style thing. Is I center at some mean and I add and subtract t. And as I vary t from 0 to infinity, I get the various sets, and then conformal picks out one set of that kind. Then the locally weighted conformal prediction is the second one, where I learn mu hat and sigma hat, and I vary those, and I pick one among them. And then I also mentioned the third one, which is this the Romano et al. Paper, which trains quantile residuals and says, well, I'm going to center at some, I'm going to use these 2 points, the alpha by 2 and 1 minus alpha by 2 quantiles. I'm going to vary t from minus infinity to infinity. And there's one t among these that I'm going to pick. And I'm going to pick this t hat based on the data using conformal prediction. So as you can see, there are many choices in the literature that fit into this nested conformal framework. And they can tell you what shapes of sets are people really looking at. So why would we want to use the language of nested conformal prediction? Well, one reason is it's somewhat natural to consider this sequence of nested sets. And the reason is that conformal prediction and its variants, they produce nested sets. As I vary alpha, the sets will actually be nested with conformal prediction. Another reason is that the optimal sets, the level sets of the conditional density, are also nested sets. And the last reason is that maybe it's easier to specify the shapes of the sets that I'm looking for rather than the scores of the residuals. It might be easy to say, okay, I would like to center at these points. This is how I'm going to scale things. I don't know the right way to scale things, but that I can find using the data. So it may be easier for some people to specify the shape. So this is another reason to use it. Now, the reason we like it is because it's very easy to define leave one out residuals. So for a general class rather than the usual standard residuals, we define Ri as the smallest t such that yi lies in this nested set at level t of xi. Okay, so we'll find the smallest t for which that holds, and so that's going to be called the leave one out residual. So where we used f minus I, which means to form that sequence of nested sets, I left out point I to form them, and then once you define the residuals in this way, it leads to a natural extension of Jackknife to new settings, for example, using the quantile regression and so on. And so you can combine the two ideas of leaving one out to gain some kind of sample efficiency, and using quantile regression, which is the really right thing you should do. You shouldn't be looking at mean regression, you should look at quantile. So you can combine those ideas now quite seamlessly. And of course, you can define split and full conformal using the language of nested sets. But mathematically, they're completely equivalent. The usual conformal prediction that I had first described and this notion of nested conformal prediction using nested sets, they're completely mathematically equivalent. But this just was a simpler way for us to define leave one out residuals. So we went by this language when we wanted to generalize things. Okay, so using that, we define what I think is the state-of-the-art method that has guarantee. So this will be, so this is on an earlier version is on archive already. A newer version will be on archive later this week. And so this, if anyone was to apply conformal prediction today, this is what I would recommend doing in practice. So it combines three distinct ideas. The first one is don't split, don't do full. We should use leave one out kind of ideas. Do leave one out Jackknife plus or cross conformal. I haven't defined cross conformal, so let's say we want to use Jackknife plus kind of ideas. The second thing is don't try to estimate the mean. That's the wrong thing to do. We want to estimate quantiles, and so we're going to use a CQR type, residual or nested set, but we're going to do it at level 2 alpha and not at level alpha by 2. And it doesn't actually matter what algorithm we train, because conformal prediction wrapper will make sure we get our guarantee at the end of it. So I can actually use, I can actually train the quantile regression at any level. And we've found that, and I can describe the intuition maybe later, but we found that training these quantile regression algorithms at level 2 alpha and correcting for them, in other words, going for under coverage and expanding the set essentially seems to work better in practice. And we're going to use the algorithm we're going to use for quantile regression is quantile forests. So this was proposed by Meinshausen in 2006, I think. So that's the second idea, is let's go for quantiles. But the third idea is we don't want to retrain this forest, and we're going to use out of bag prediction. So when we look at what if I left the ith point out, we don't have to retrain the forest. We just look at all of those trees in the forest that left out the ith data point. We can get out of bag predictions. We can get out of bag residuals, and all of this goes through. So essentially, these are three kind of distinct ideas that you can, that have been explored separately in the literature. And once you put them together, you get extremely good, performance in practice. So maybe I won't describe what are the methods we compare to, but SQC is split quantile, and SC is split conformal. OB is out of bag with cross conformal. So things like that. But the last one is what I just described, which is you use OBs out of bag predictions, and QCC is you do quantile cross conformal predictions. So you use quantile random forests and you use cross conformal. The cross conformal is slightly different from Jackknife. We think you should always use cross conformal over Jackknife Plus, but it's a little harder to describe. Somehow Jackknife Plus is a little more intuitive and easy to describe. But as you can see, in terms of coverage, all these methods get the same coverage. But in terms of width, at least on these data sets that we show you, get better width. But across a wide variety of other simulations and other data sets also, we get the lowest width. And we don't pay a computational price because we're not retraining. We train one forest. We don't have to retrain them n times when we're doing these out of bag predictions. So there's been a lot of work actually that looks at this, variants of these ideas. So some of these, they look like Swedish names to me. So Bjorstrom, Linusson, Ljofström, Johansson, Carlson, Ekland, or a lot of them over the last 6 years have been looking at out of bag ideas. Using ensemble technique somehow is really good for conformal prediction, lends a lot of stability to the resulting procedures. Using cross conformal is a good idea because it's sample efficient. So they've been combining some of these ideas, but they've not used quantile regression. Somehow they've all been going after mean regression, so it's doing something slightly different. Similarly, the Kim Shu Barber paper in that was just released, same kind of thing. They've not been able to combine all three ideas, and so they usually do A plus C, that is cross conformal or Jackknife Plus, with out of bag, but they do it with mean regression. And that's just not the right idea when you have asymmetric or heavy tailed problems. You're going to have instabilities from mean regression that are much better captured from, or the asymmetries in the distribution are much better captured by quantile regression. And so now using this framework, we can get all three together. And as far as I know, this is the state of the art. So if anyone's going to ever implement it, we'll put up code online later this week or next week, and people can try it out on their problems. You can, of course, you can use this with neural nets if you want to. But the out of bag predictions, I mean, these neural nets will become expensive to retrain n time. So if you were going to use neural nets, I would use split conformal prediction. It's the easiest and cleanest for neural nets. But if you have something like forests, where in some sense out of bag is for free, then I would use forests. I think they work beautifully in real data. Okay, so I'm ready to end and summarize. There's some, I skipped many topics. We have some work on handling covariate shift, approximating conditional coverage. Dan asked some question about adaptivity results. Can you prove more, making further assumptions? Yes, you can. And applications of this to other problems, which are not just predictive inference, like clustering and change point detection. So there's been some other work if you're interested in these areas. Here are some, some open problems that I think about from time to time. What do we do for binary classification? I have some work coming up later this summer on that problem. Algorithm selection, if you have many algorithms, can I use this to choose the best one? You can use it as a heuristic. You can produce prediction intervals for many algorithms and choose the one that has the shortest width and average. That's a heuristic. I don't know any assumption-free guarantees for algorithm selection using conformal prediction. So that's an interesting problem to think about. Again, adaptivity to parametric assumptions. I think there's plenty to think about. What about Jackknife Plus? It seems to be more stable than we're able to prove. Can you make some assumption further and show that it actually gives you smaller width or the same, oracle coverage, anything of that kind? Can we get analytical expressions on width and volumes of in special cases? Maybe. and perhaps extending this to new settings. There's been some work on a streaming setting, but I think a lot of these ideas are, if you want to go distribution free or assumption free, a lot of these quantile based out of sample residual ideas are applicable in other settings as well. Here's a quick summary of the theoretical results. The naive methods have no assumption-free coverage, and they have bad, empirical performance. Split conformal gives you theory and good empirical coverage. Full conformal gives you theory, but overfits. Sometimes if it's a very powerful regressor. Jackknife has no assumption-free theory, but often gives you 1 minus alpha in practice, but smaller if unstable. Jackknife Plus gives you 1 minus 2 alpha in theory, but 1 minus alpha in practice. And it says here's a summary of computation times, but I won't go through them. I mean, we went through a lot of the empirical observations in practice, but I'll just emphasize the last point. The state-of-the-art method combines the leave one out idea with quantile forests, with out-of-bag predictions. And so these are kind of three different things. How do you design the residuals? How do you make it computationally efficient? How do you do it leave one out to make sample efficient? Combines all of them to give you a provable guarantee algorithm that also gives you kind of empirical conditional coverage and provable marginal coverage as well. Again, I'd like to quickly thank the Baccarati group. I've learned a ton from all of them. It's been a pleasure working with them, and we continue to talk. I'd like to thank AIM, the American Institute of Math, where this collaboration actually started. And I'd like to thank Arun and Chirag, who have been working with me on the recent topics of the state-of-the-art algorithm, nested conformal prediction, and so on. I'd like to end and thank all of you for staying till the end. Sorry, I meant a few minutes over, but I'm happy to stay on for a few questions if people have questions.
All right, thank you, Aaditya. So we have 2 minutes for questions. Any quick questions?
Maybe I'll stop on this slide because it's better to thank my collaborators.
All right. I guess if there are any more questions, please feel free to reach out to Aaditya. And thank you again for giving the talk.
Yeah, thank you.